Okay, now we're working on the optimal portfolio case 2. And in this case, what we're going to do is we're going to look at two risky assets that have perfect negative correlation. This is probably the least likely to happen, all right? But it's important to think about because of what we're going to be doing here over the next, over case 3 and case 4. Let me explain here. So let's say we have two assets, asset A and asset B here, okay? And let's say you want to put some of your money in asset A and some of your money in asset B. If I were to ask you, let's say you put 50% in asset A and 50% in asset B, again, you have expected returns on the y-axis and sigma on the x-axis. If you were to put 50% in A and 50% in B, where would you be on this graph? Many of you would say you'd be somewhere right in the middle at P. Well, that's actually not true. And the reason is that's not true is because of the statistical property that the variance of A plus the variance of, the variance of A plus B is equal not just to the variance of A plus the variance of B, but it's also equal to the variance of A plus the variance of B plus 2 times the covariance between A and B. Okay? So this is a super important statistical property that exists. Notice that if we have negative correlation, right, where negative correlation means that we have negative covariance, as A goes up, B goes down, and as B goes up, A goes down. You can think of maybe energy, some energy stock and the rest of the stock market, something like that. If we have negative covariance, then the portfolio of asset A and B, the variance of the portfolio of asset A and B might be lower than the variance of A plus the variance of B. In fact, it's possible that the variance of the portfolio of A and B could be lower than either the variance of A or the variance of B. Let me show you what this might look like graphically. So if I draw a line from A to B, okay, what happens is when the covariance becomes negative, this line begins to bend towards the origin. Does that make sense? And the more negative the covariance, the more the bend towards the origin. Recall from a previous video that we want to be up here in quadrant 1 to the extent that we're risk averse. We want high expected return for a low level of risk. So we want to be up here in quadrant 1, and when the covariance between the two assets in the portfolio are negative, we start to get there. In this particular case, when we have perfect negative covariance, what's going to happen is this thing's going to reach all the way to the origin. That is, we are going to find a portfolio where basically we change the weights until we get to this point here where we have no risk, there's zero risk, where there's this tangency between this curve and the y-axis. Okay, so the idea of having two risky assets with perfect negative correlation, it doesn't really exist in the real world. However, it's important to help us understand what's going on. And for fun, let's do some math. Okay. So recall the variance of A plus the variance of asset A plus B is equal to the variance of A plus the variance of B plus 2 times the covariance. Or let's assume that we have two assets, two risky assets. We have risky asset D and risky asset E. Let's just for some vernacular assume that D is debt and a debt instrument, say a bond, and E is an equity instrument or a stock. And so that the riskiness of D is less than the riskiness of E, all right? So the variance of a portfolio made up of a risky asset D and a risky asset E is going to be equal to the weight squared of D times the sigma squared of D, that's the variance of D, plus the weight squared of E times the variance of E, that's going to be the variance of E, right? Or yeah, the second asset, times 2 times the covariance. Well, we have to include the weights here because we're weighting these things differently, right? We have to include the weights here. And notice here that that rho, the correlation coefficient, is equal to the covariance of E and D divided by the variance of E and D. Let me highlight this. This will be important. Okay. So what I'm going to do here is I'm going to substitute in rho here times, so I'm just going to multiply both sides by the product of these two variances. And what I get here is now I can substitute rho times the product of those two variances in for the covariance of E and D. So we get this formula here. Okay. And if rho, the correlation coefficient between E and D, equals -1, then what can happen is this positive sign becomes a -1. I'm going to just put that negative sign out there in front, and I don't have rho anymore. And it can be shown that the variance of the portfolio will eventually become, I'm just doing some quick algebra here, will eventually become this formula. Okay? If I take the square root of both sides, I get the variance of the portfolio is equal to the weight of D times the variance of D minus the weight of E times the variance of E. Okay? So eventually that happens, and that's going to be important going forward here. All right. So what I want to do here is I want to try to get to that tangency where the variance of the portfolio between the two assets is equal to 0. So I'm just going to set this equation equal to 0, and I'm going to solve for WD, the weight of asset D, and I get the following. Okay. I just did some algebra. I'm setting this thing equal to 0. I'm doing some algebra. I'm adding both sides here. And then I'm solving for the weight of D, and I get the weight of D is equal to the weight of E times the sigma of E divided by the sigma of D. Okay. We also know that the weight of E is equal to 1 minus the weight of D because we only have the two assets in our portfolio. We're going to use some algebra, and eventually we get the following. And these are the equations that you'll be interested in. The weight of D, the optimal weight of D, I should have put, in fact, let me do that. The optimal weight of D, I'm going to put a star there to show you that that's the optimal weight of D, is equal to sigma of E over the sum of the sigma of D and the sigma of E. Likewise, the optimal weight of that we should put into the equity side of the portfolio is going to be sigma of D over sigma of D and sigma of E. Okay? Let's do an example here real quick. If I can type. Seriously, if I can type. Let's assume the following. Let's assume that the expected return of D is equal to 6%, and the expected return of E is equal to 15%. Let's also assume that sigma of D is equal to 3%. Listen, I'd start this video over, but I've been making videos for like 36 hours straight. And so you're just going to have to deal with my my inability to type. Sigma of E, let's assume that sigma of E is equal to 8%. Okay? So this information is given. All right? Going back up here, the optimal weight of D is straightforward. The optimal weight of D is equal to sigma of E divided by the sum of the sigma of D and sigma of E. So that is 8 divided by 11, which is equal to 0.7273. And the optimal weight of E is going to be equal to 3 over 11. or 1 minus that, which is equal to 0.2727. Okay? So in the case that you ever find two perfectly negatively correlated risky assets, you're going to use these formulas to optimize your portfolio. That is, to change the weights that optimize the portfolio. And in the example that we've given below, we've found that the optimal weight of D is 0.73 and the optimal weight of E is 0.27.